Hello, my name is Tangi Beverly, and this is my last research video for History of Mathematics this spring semester 2017. My video is about the history of Fibonacci numbers. Now I will be discussing about who discovered Fibonacci numbers and how. Then by showing series of examples how it is represented in nature and other areas in our lives. What is Fibonacci numbers? It is a series of numbers where a number is found by adding up the two numbers before it. Starting with 0 and 1, the sequence goes 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. The Fibonacci sequence is named after Leonardo of Pisa. His nickname is Fibonacci. The Fibonacci numbers were first introduced in his library of Bocce. His father was a Parisian merchant and they traveled widely around the world. Math was amazingly important to those in the trading industry, and his passion for numbers was cultured in his youth years. It is said that numbers have first originated in the Hindu Arabic arithmetic system, which Fibonacci studied while growing up in North Africa. In 1200, he returned to Pisa and used the knowledge he gained from his travels to write Library of Bocce. It was published in 1202. He introduced the Latin-speaking world to the decimal number system. He wrote many books about geometry, commercial arithmetic, and irrational numbers. Fibonacci also helped develop the concept of zero, and his contribution to mathematics is for the sequence of numbers that appear in Library of Bocce. The problem with rabbits. Fibonacci first noticed the sequence when thinking about a mathematical problem about rabbit breeding in Library of Bocce. Suppose a pair of rabbits, one male, one female, are put in the field. Rabbits can mate at the age of 1 month, so at the end of the second month, a female can produce another pair of rabbits. So what if rabbits never die and that the female always produce one pair, one male and one female, every month for the second month and so on? At 2 months, the rabbits have mated but not given birth, resulting in only one pair of rabbits. At the 4th month, the original pair gives birth again, and the second pair mates but does not yet give birth, leaving the total at 3 pairs. This pattern continues until a year has passed, in which there will be 233 pairs of rabbits. So if there are Sn pairs of rabbits after n months, the number of pairs in a month, n plus 1, will be Sn plus the number of new pairs born. But new pairs are only born to pairs at least 1 month old. So there will be Sn minus 1 new pairs. So we have Sn plus 1 equals Sn plus Sn minus 1. The rabbit problem is obviously false, but the Fibonacci sequence does occur in real populations. The honeybees provide an example. In the colonies of honeybees, there is one female bee known as the queen. The other females are worker bees, unlike the queen bee produce no eggs. The male bees doesn't work and are known as drone bees. Males are produced by the queen's unfertilized eggs, so male bees only have a mother but no father. All the females produce when the queen has mated with a male and so have 2 parents. Females usually end up as worker bees, but some are fed with a special substance called royal jelly, which makes them grow into queens ready to go off to start a new colony. When the bees form a swarm and leave their hive in search of a new place to build a nest. Female bees have 2 parents, a mother and a father. And the male bee only have 1 parent, a mother. So if you break this down in a chart, the male bee has 1 parent that is a female, so he would have two grandparents since his mother had two parents, a male and a female. He has three grandparents. His grandmother had two parents, but his grandfather only had one. Again, we can see the Fibonacci sequence. As I stated earlier, we know the rabbit problem is unrealistic, but Fibonacci numbers do appear in nature, such as the example of the bees. Fibonacci numbers also appear in sunflowers, hurricanes, and galaxies. Sunflower seeds are arranged in the Fibonacci spiral, keeping the seeds consistently distributed no matter how large the seed head may be. Nature seems to use the same pattern to arrange petals around the edge of a flower and to place leaves around its stem. A Fibonacci spiral is a series of connected quarter circles drawn inside an array of squares with Fibonacci numbers for dimensions. The squares fit perfectly together because of the nature of the sequence, whereas the next number is equal to the sum of the two before it. Any two successive Fibonacci numbers have a ratio very close to the golden ratio. The larger the pair of the Fibonacci numbers are, then closer to the approximation. The spiral and resulting rectangles are known as the golden rectangle. The golden ratio. If we take two numbers in the Fibonacci series, dividing each by the number 4, we will find the following series of numbers: 1, 2, 1.5, 1.666, and etc. If you plot a graph of these values, you will see that they seem to be tending to a limit, which we'll call the golden ratio, also known as the golden number and golden section. The golden ratio is denoted by the Greek letter phi. The number phi are irrational numbers. After two turns through a half a circle, we will be back to where the first seed was produced. Over time, turning back half a turn between seeds will produce a seed head with two arms rotating from a crucial point, leaving lots of wasted space. Something similar happens for any other simple fraction or term. Seeds grow in the spiral arms that leave lots of wasted space between them. The best value for the terms between seeds will be an irrational number. Not any irrational number will work. For example, the seed head created with 5 turns per seed seems to have 7 spiral arms of seeds. This is because 22 divided by 7 is a very decent rational approximation of pi. A rational number is needed in order not to waste space, but this is not well approximated by the rational number. This is why a turn of pi gives an optimal packing in seeds and leaves and plants. It also explains why the Fibonacci numbers appear in the leaf arrangement and as number of spirals and seed heads. Fibonacci numbers give the best approximation of golden ratio. They can take turns at being the denominator of the approximations and define the number of spirals at the seed's heads. Increased in size. The golden rectangle does appear in the Mona Lisa and other Renaissance artworks. Fibonacci numbers are used in the field of computer science, which are known as Fibonacci heap. It's a heap of data structure similar to the binomial heap, only with a few modifications and a looser structure. The Fibonacci heap was designed in order to improve the shortest path algorithm from big O m log n to big O m plus n log n by optimizing the operation used by the algorithm. Fibonacci sequence is used in the complexity analysis of its operations, similar to the binomial heap. A Fibonacci heap is a collection of heap-ordered trees. They do not need to be binomial trees. Each tree has an order, just like the binomial heap, that is based on the number of children. Nodes within a Fibonacci heap can be removed from their tree without restructuring them. So the order does not necessarily indicate the maximum height of the tree or the number of nodes it contains. The pointers between nodes in a Fibonacci heap are very likely that of the binomial heap, only that each node in the Fibonacci heap contains a double linked list of all the children. This allows node removal and child list concatenation to both be performed in linear time. Marked nodes are an important part of the Fibonacci heap. Is how it is marked nodes within the trees. The decrease key operation marks a node when the child is cut from the tree. This allows us to track some history about each node. The marking node allows us to track whether the node has no children cut, unmarked it. The node has been a single child cut, marked it, and the node is about to have a second child cut, removing the child of a marked node. Fibonacci search is also connected to the field of computer science. Fibonacci search technique is a method of searching a sorted array using the divide-and-conquer algorithm that narrows down a possible location with the aid of Fibonacci numbers. The human face overflows with examples of the golden ratio, known as the golden section, as I stated earlier in my research video. The head forms a golden rectangle with the eyes at its midpoint. The mouth and nose are each placed at the golden section of the distance between the eyes and the bottom of the chin. From the view from the side, the human hand illustrates the divine portion. The first golden section from the front of the head defines the position of the ear opening. The successive golden section defines the neck, and the back of the eye, and the front of the eye, and the back of the nose and mouth. The dimensions of the face from the top to the bottom also exhibit the divine portion, and the position of the eyebrow, nose, and mouth. To sum up my research, Fibonacci numbers were discovered by Leonardo Pisa and named after him. Throughout his youthful years of traveling, he gained knowledge of mathematics and soon wrote a book, Liber Abaci. That is where Fibonacci numbers examples appear in his book. The problem with rabbits was unrealistic, but get him started discovering the Fibonacci numbers. Fibonacci numbers are present over the nature and artwork, such as sunflowers, hurricanes, planets, galaxies, Mona Lisa, shells, and etc. The number 5 are irrational numbers, which are the golden numbers and the golden section. We learn why Fibonacci numbers appear in leaf arrangements and as the number of spirals and seeds has. We assume that this are the ratio of successive Fibonacci numbers. Eventually settles on the golden ratio. Evolution gradually settled on the right number as well. Fibonacci numbers lies in the heart of nature in our number system. They also exist in the field of computer science, such as Fibonacci heap and the Fibonacci search. Thank you for watching my video about the history of Fibonacci numbers for my History of Mathematics course.